Okay, good afternoon, everybody. This is the first lecture on the C programming language in this course. So the rest of this course is all going to be taught in the C programming language. Right. And so I guess I should tell you what C is. Most of you probably already know. But C is a general purpose compiled procedural programming language. Right. So procedural meaning it has structured programming constructs like loops, conditional statements, and functions. So in that respect, it sort of resembles Python as you were taught it in 121. It has a static type system, so that's similar to what Java has, right? So variables in Java have a type that's known at compile time. C is similar. It has recursion, so that's, I guess, useful. C is often referred to as the high-level programming language that is as quote-unquote close to the machine as possible. So what that means is that the abstractions you get in C generally map onto machine instructions that your CPU can perform natively, right? So for example, C provides a type that's called int, which represents an integer value. Right? On most modern CPUs, the int type in C will map directly onto one of the types that your CPU natively supports, right? Similarly with double and your other types as well. Most of the programming constructs in C essentially map almost one-to-one from C to a machine instruction of some kind. Right? So it doesn't provide any sophisticated data structures like Java or Python does, right? So if you want a list, you don't have a list in the standard library. You have to write your own. Okay, so there's a link here that takes you to the history of C as written by its creator. Someone by the name of Ken Thompson. If you're interested in the history of programming languages, that is actually a very interesting read. It might be, some of the details in that might be lost on you right now because you haven't taken a lot of computing science courses yet. So some of that article you won't understand. I don't think you'll understand anyway. But when you when you've taken more computing science courses, you've learned more about architecture and things like that, and compilers perhaps in fourth year. This article makes a lot more sense. But it is an interesting read on the history of C. I'm just going to grab a few snippets from that article. Ken Thompson is the creator of C. He basically wanted to create a computing environment. He wanted to make his own computing environment. So he wanted his own programming language. He wanted his own operating system and things like that. Right. And this was back in the early days of computing. So like 1968. So computer hardware was very primitive compared to what you have today. Right? And you used to be able to do this sort of thing, right? So you used to be able to write your own operating system and create your own programming languages and all sorts of other things. You can still do that today. Most people don't do that today anymore. All right, so the interesting thing, so this was back in the early days of computing. So the computer that he was working on is by today's standards extraordinarily primitive, and even in the time that he was working in, was considered not state of the art. Right, and so the computer he was working on was this thing called the DEC PDP-7. So DEC is the Digital Electronic Corporation, I think. I don't know if they're in business still or not. If they are, it's just their name. It's not the actual company anymore. So the PDP family of computers are well known. They're quite famous. So the amount of memory that he had to work with, so that's 8 kilobytes, roughly. 18-bit words, so roughly 16 kilobytes, right? Your cell phone probably has 4 or 8 gigabytes of memory, right? So that's funny, right? That's like millions of times smaller than what your cell phone has in terms of memory, right? Notice he had no software that was useful to him, right? So he has this computer, which you'll see in a second, was this giant machine, no actual software, right? And he's trying to create his own his own computing environment. So he's stuck doing this without an actual programming language. Well, without a high-level programming language. Instead, he's working in this thing called assembly language, which more or less looks like plain English, but you're basically writing in machine instructions, right? The instructions that your machine actually understands. That's the computer he was working on, right? So it's this giant box here. It's got a bunch of electronic looking things on the front, right? That he's got it looks like a keyboard over here. Notice there's no monitor, right? That's actually a printer that's attached to there. That machine there, when it first came out, was $72,000 US. That's $600,000 today, right? And it's only got 8 kilobytes of memory on it. It's actually worse than this. So if you read the article, he talks about how you actually had to program this thing, and how you had to transport a program and put it on this computer, right? Essentially, you took a paper tape that had holes in it punched into it, and you would feed it to the computer, and something would be able to read the tape and understand, and convert that into instructions that the machine can understand. Okay. All right, so this is the machine he's working on. So he makes surprisingly fast progress over a relatively small number of years. Right? Remember, he's got no programming language. He's got no operating system. Right? So he starts, not really starts, but in the process, he creates this language called B. Right? And in that language, he invents the operators plus plus and minus minus that you know from Java. Right? So that's where those two operators came from. After working in B for a while, he decides that this language really isn't doing what he needs it to do, so he created C, right? Which kind of makes sense because it comes after B, right? And so him and this other fellow named Dennis Ritchie started to work on the Unix kernel. Right? And so the reason they're writing C is so that they can actually write their operating system. So they're creating a programming language so that they can create their operating system, and whatever other tooling they need. Right. So starting in '69, in 1973, they basically completed their C programming language. Right. So most of the modern C programming language was now done in 1973. Right. So keep that in mind. Right. So that's 50 years ago now. Right. And so that's the language you're going to learn about. Right. So the language you're learning about was more or less complete 50 years ago. And then 5 years later, they finally published this book. You will sometimes still see this book being used as the reference book for university courses on the C programming language, right? Which is crazy, right? That's from 45 years ago. All right, so the modern version of C looks a little bit different than that, than the original version of C. So eventually C got around to, well, I guess the rest of the world got around to standardizing C. Right, so some organizations, ANSI and ISO, decided that we should standardize. Well, they didn't say. They undertook the process of standardizing the language. Right, so they wrote an official documentation describing what the language looked like. Right, there's a committee that takes care of the C programming languages. People suggest additions and removals and things like that. The committee decides whether or not that should happen. Right, and then there have only been a few updates since then. Right, so 89 was the first standard. 99 was the second standard version of the language, right? So 10 years later, 12 years later was the next update, and then 6 years later was the next update, and that only has very minor updates compared to C11. There is a C 2023, I believe, that adds some additional features to the language. But compared to modern programming languages like Python and Java, the C programming language evolves very, very slowly. Right. So Java changes every 6 months now. I don't know when the next update to the C programming language will be, but it's probably not going to be for several years. Okay, so where's C used? So it's a general purpose programming language. It's probably, as far as general purpose programming languages go, it's probably the most commonly used language across all programming, as a general purpose programming language. Right, so you can use it basically, you can use it for most tasks. It's not the best language for all tasks, but you can use it for most tasks. Right, almost every operating system that you use, so Linux is all C plus a little bit of other stuff. Windows is mostly C with C++ and assembly. So embedded systems, so these are your small computers that don't necessarily have a screen and a keyboard. So they're the computers that you show up in little devices. Most of these are programmed in C. Most of your high-level programming languages like Python, They're all implemented in C, right? The Java virtual machine is, I don't know if it's implemented in C or not. Probably is, right? Languages like Perl and Ruby, PHP, and many other interpreted programming languages, they're all implemented in C. So C is basically everywhere, and that means most modern programming languages are able to use C libraries, right? So you can take a C program or a bunch of C functions, compile it into a library, and most of your modern programming languages can call those C library functions. Right, that includes Python and Java. Right. Anything that's computer graphic intensive is probably written in C or C++. C Sharp, I guess, if you're on Windows. Anything that's computationally intensive probably has some C in it. C or Fortran. Anything else? C++, I guess. And many other places, right? It really is usable for almost every task. Again, not necessarily the best language for every task, but it is usable. TIOBE is this organization that ranks the quote unquote popularity of programming languages. By popularity, they just mean how many questions are being asked by these on places like Wikipedia or Stack Overflow and other search forums. C has never been ranked lower than number 2 since 2001. Right, if you actually look at the current TIOBE index, which I have open somewhere here, right? So Python is currently at the top. C is 2, C++ is 3, and C Sharp is 5. Right. So if you consider C, C++, and C Sharp all to be all to represent a family of related C-like languages, they're the most popular languages in use currently. Java's fallen to 4, which is interesting. All right. Okay, so you have to program in C, and that means you need a C development environment on your computers. If you followed the instructions at the beginning of the year for setting up your computers, you should be good to go. So on Windows, you can use Visual Studio Code as your editor. You can use Eclipse. Wait, can you use Eclipse? I don't know how easy it is to use Eclipse because you have to use it through your Linux subsystem. You might be able to use Eclipse. I'm not 100% sure. I think you can. I think you can. I think that works. I think I tested it. So you can use Visual. You need a text editor of some kind. Visual Studio Code is, I guess, it's pretty good. You can install plugins that understand the C language. It's available everywhere. So you might want to consider using that. You don't have to. You can use some other text editor if you want. Right. If you want to do any debugging, the Eclipse debugger is actually pretty good. It's much easier to use than the command line debugger that you'll have to use if you want to use Visual Studio Code, for example. Documentation. So unlike Java, there is no standardized online documentation for the language, other than the official standard document. But that's not really a good. It's not really an easy piece of documentation to read. So these 2 links will take you to links that describe both the language and the entire standard library for both languages, for C. Okay, so what does a C program look like? It's just plain text, so it's a bunch of files. So a simple C program, so a really simple C program is made up of just one source code file, right? And so the standard extension is .c, right, or .big C. So if you see a file that ends in .c, it's probably a C source code file, right? So it's just plain text containing the C programming, containing a C program. If you have a slightly more complicated program, then your program probably also has these things called header files, which are also plain text, right? And they will have the extension .h or .H, right? So basically, your program is a collection of text files that either end in .c or .h. Like Java, if you want to run your program, you need a main function somewhere, right? So Java needs a main method to start running. C needs a main function somewhere. Funny thing about C is you can only have one main function in your entire program, right? And its name, you only have one thing named main in your entire program, right? And if it's a main function, that's where your program will start running from. Right, so this is the Hello World program. This is one version of Hello World in C, right? So you see there's this statement up here that starts with a hashtag, right, and says include. There's our main function there. Sort of looks like the Java main method, sort of, not quite, right? This is one way to print a string in C, and there's a return statement here, right? Notice that C, like Java, is a brace delimited language, right? So C, because you know Java already, you already know the basics of the C programming language, right? If you wanted to create that program, it's easy, right? You just open up your text. So if you're on Windows, you go into Linux, right? You start up code inside Linux somewhere, and then you just start typing in your program, right? So it's going to look something like include standard io.h, something like that. Then int main void puts. Oh, sorry. And then return 0. Right, and that's it. There is your hello world program written in C. Right, save your program. Now you can't just run this thing like you can in the, well, sorry, if you're in Eclipse, you can in fact run this thing. Right, you just click the run button and Eclipse magically does everything for you. Right, so it compiles your program. If your program compiles cleanly, it runs your program. If you're doing this yourself in a text editor like Code, I haven't tried it, but there's probably plugins for Code that will also compile and run your program for you, right? But you can do this from the command line as well. So from the command line, you would do the following. Did I save it somewhere? Yeah. So there's hello.c, right? There's also hello1 and hello2. Those are the versions of Hello World that are in the notebook. Right? So the way you compile this thing from the command line is you run the compiler. So the compiler you're using in the course is probably GCC, right? That's the GNU compiler toolchain. And so in this particular case, we can just write gcc hello.c. Press enter. You want to see no output when you run the compiler, right? If the compiler prints some stuff, it's trying to tell you something went wrong, right? Either there's an error or some kind of warning, right? So you've done something either completely incorrect or something suspicious, right? In either case, you should go back and edit your program to remove the warnings or the errors. If there's errors, you can't run the program. I didn't get any errors, so what ended up happening was we ended up getting this file called a.out, right? If you read that History of C article that I told you about, you will learn why this thing is called a.out, right? And it's still called a.out 50 years later, right? So now you can run your program. Notice it's executable. Sorry, I should do that. Right. Oh, I don't know what K does. Okay, so notice that it is executable, right, to everybody. So the output, the resulting file that's output by the compiler is a runnable program, right, or a runnable command. And so you can now run it just by typing /a.out, and it prints hello world, right? And so this is the process that you'll go through when you're writing your C programs, right? Write the program, save it, compile it, debug it, right? Save it, recompile it, right? You have to recompile every time you make a change. Right. So for example, let me get rid of the semicolon, right? I'm going to recompile. So GCC, hello. Come on, hello.c. Right. Okay. So there's an example. If you where the compiler emits a message of some kind, right? In this particular case, it's an error, right? And so it has not successfully compiled the program, which means I can't run the recompiled program, right? It's telling you, hey, there's a semicolon missing there, right? Okay, so fine, you go back to your program, right? You put in the semicolon, you resave your program, you go back, you recompile, right? No output from the compiler. There's a.out, so I can run that, right? And away you go. If you don't want it called a.out, you can tell the compiler to call it something else. So GCC hello.c minus O. So that's minus O tells it to name the output file something else. Right. So I'm just going to call it hello. ls. Now there's hello. right? It doesn't delete a dot out, right? It's still there, right? But hello is also there, and it does exactly what you expected. So writing a C program is generally this process of editing the file, saving the file, compiling, repeat the process. There's another version of Hello World. So the only change here is the function that was used to print out the message. So this version uses this function called printf. This is a little bit more complicated. Printf is the formatted print function in C. Actually, there's a whole family of functions that are named something like printf. They all deal with producing formatted output, right? So by formatted output, I mean this thing here, called the formatting string. It tells printf how to treat all the other arguments that are passed to the function. So that %s says treat the next argument that's passed to the function as though it were a string, or format it as though it were a string. Right? The \n is the new line character, so that means print a new line after converting that to a string. Right? So that prints hello world and then goes to the next line. Right? Puts goes to the next line automatically for you. Puts can only handle strings though. Right? Printf can handle anything you pass to it. So if you pass it an integer, you can tell it to convert the integer using a different conversion here. Right? It can handle floats and doubles and so on and so on and so forth. Right. Okay, so what exactly is compiling? Right. So most of you, well, many of you probably haven't actually manually compiled a program before. Java technically is a compiled language, but because you're taught using Eclipse or some other IDE, the IDE takes care of the compilation for you. Right. So compiling is the process of transforming code written in one language to another language, possibly the same language, which seems weird, but you can compile a language into itself. Most of the time when people say, hey, I got to compile my code, they mean taking your code and turning it into something that the machine can run directly. Right. So that's normally what people mean. In Java, you have to compile your source code, right? So in Java, your .java files get turned into something called bytecode. In Python, all of your Python files actually do get compiled, right? So if you ever look in the folder containing your Python files, you'll probably see a .pyc file. That's the compiled version of your Python file, right? So Python is also compiling your stuff for you as well. Compiler is simply a program that actually does the compilation process. Right. Now there's a whole bunch of, there's many compilers. Are there many? There are not that many. There are several compilers that you can choose from. Right. It's hard to write a compiler. There aren't that many of them. Right. So there's several that you can choose from. If you're on Linux, you're probably using GCC. Right. So install GCC if it's not there already. If you're on Mac, I'm pretty sure it comes with CLang already. I think it does. If not, just follow the instructions that are on cue. It tells you how to install everything. Right. You can also use CLang on Linux if you want to. Right. So if you prefer to use CLang, go ahead and use CLang. You can install that as well. Right. It's open source and freely available to you. Okay, that's how you compile your programs. Right. So that's compiling hello 1 and hello 2. Right. I'm using the -o option here to save them as hello 1 and hello 2. Oh, I should show you what happens if you don't. So, okay. So there's a.out here, right? If you compile anything else and you don't tell the compiler what to save the file as, it's just going to overwrite a.out. Right? So if you have like 5 programs in your directory and you compile them without renaming them to something else, it's always going to, the compiler will always overwrite a.out. Right? So if I compile hello 1, right, its output goes to a.out. Which you can see if I actually print out the time, right? So 1242, I guess not close enough, right? My clock time is off compared to that, right? But that's the most recent file that was just produced, right? So that's actually hello 1 that has been compiled and saved, right? So you have to be careful here. If you're not renaming your output files, you're always going to overwrite the same output file. The compiler will blow over whatever, will always overwrite the output file without warning you. Right, so suppose I save this as hello. right? It doesn't warn you that it's going to overwrite hello. It's just going to overwrite it. So do watch out for that. That might catch you by surprise. Right, and of course that produces the compiler, if you run it that way, generates a runnable program, assuming your program compiles without errors. And so you can run them as though they were just a regular command. Okay, so what else is going in that program? Well, there's this include thing. Right, notice the first line of my program was this include directive. Right, okay, so that include directive is what's called a preprocessor directive. So the compilation process in C goes through a whole bunch of steps. Often the first step is the compiler runs something called a preprocessor. The preprocessor is a program that takes your C source code file and transforms it into and transforms the C source code file into another C source code file. Right? So it actually transforms your C source code file. So what it does is it does things like it removes the comments from your source code, right? Anything with a hashtag in front of it is trying to tell the preprocessor to do something. So hashtag include tells the preprocessor to take the contents of standard.io.h and drop that into your program, right? That's exactly what it's doing, right? So include tells the preprocessor to insert the contents of a file into your source code file, right? So you can include, if you wanted to, some other file that you had kicking around that contains some code that you want into your program using that include directive, right? The thing here, so the thing inside of the angled brackets, standard.io.h, that thing there is the header file that contains the standard library functions, not the story, that contains the declaration of the standard library functions that perform input and output, right? So if you want to print something, you need either printf or puts, right? That function declaration lives in standard.io.h, along with several other function declarations, right? So let's see what happens if we don't have that line. Right, so if I comment out that line, comments in Java in C work exactly the same as comments in Java. Right, so I comment out that line and try to recompile my program. Hello. Okay, you get a warning, right? It says something like implicit declaration of function puts, right? And so the compiler is trying to tell you, you're calling a function, I don't know what it is. That's essentially what it's telling you, right? So it doesn't know what that function puts actually is. So it knows it's a function because you're calling it with the function syntax, right? You've got the name followed by the round brackets, right? But it doesn't actually know what arguments should be passed to puts. It doesn't know if puts returns a value. It doesn't know anything about puts, right? Surprisingly, though, it's not an error, right? It actually did work, right? I can actually, here, let me remove a.out and recompile, right? So I got this warning, but it actually does produce a.out, right? So it actually does compile your program. It actually does run, right? Which is strange, but it does work. Okay, so generally you should tell the compiler what are the functions that you are using in your program, right? What arguments do they have? What values are they returning, right? And the way you do that is you include the header file where those functions are declared. Right. So by including that include directive, right, the compiler now knows, oh yeah, there's this thing called puts. It takes a string as its argument. Sorry, right? I can compile that cleanly without any errors, right? And you can run your program. Oh, sorry. I'm going to come back to this in just a second. I think. Yes. All right. So comments in C are exactly the same as comments in Java. The original commenting style was the /*//, right? So the multi-line comment. In C99 added the end of line comment as well, right? So the // is actually the newer style of commenting, and it's the /*, which was the original style of commenting, right? But they both work the exact same way as they do in Java. Every C program needs a main function to run, if you want to run the program. There has to be exactly one main function. So if more than one of your C source code files contains a main function, you have a problem. You can't actually compile that program, right? Sorry, you can compile it. It won't link. So it won't produce a finished program. This is true, assuming you're compiling for what's called a hosted execution environment. Right now, you don't actually have to worry what that is. That's basically any normal computer, right? So any standard computer that supports the full standard library is going to start running from this function called main, right? You might have a computer, you might be compiling a program for a computer that doesn't support the full standard library, right? So for example, most embedded devices do not support the full standard library, right? There's no standard out, so it doesn't make sense to print something to the screen if you've got this little chip somewhere in a device that doesn't have a screen, right? So those types of those programs can start running from somewhere else, right? But the compiler writer has to decide where that's going to start running from. So in C, your main function can look like that, or it can look like that. Right? The second one looks sort of like the Java one, right? Not quite, but sort of, right? The first one is the simpler form, right? So the first version of main has no parameters, right? That's what the void means here, right? The int means it returns an int. So that's also similar to what Java would look like, right? That's the version of main that you write if your program is not taking any input from the command line. Right, so you can write a C program that accepts command line arguments, right? Just like you can write a bash script that accepts command line arguments. If you want your program to accept command line arguments, it's the second version that you need to use. Right, argc is the number of command line arguments plus 1. We'll talk about more. We'll talk about that later on. This thing over here looks funny, right? That looks a bit strange. You might guess that the square brackets means that this thing is an array. You would be correct. So this thing is saying that argv is an array, right? What is an array of? It's an array of this thing here, char star. We'll tell you what char star means in a day or two, right? In either the next lecture or the one after reading week, right? Not important right now. This is just for information for the time being. The C standard says that the compiler writer can add extra versions of main if they want to, but now it depends on what compiler you're using. Right, so those are the two that it will be using in the course. So there's our main function in hello 1, right? Returns an int, has no parameters. Puts is a function that can print a string. When it prints a string, it adds a new line to the end of the string. So that prints hello world on one line, then goes to the next line. It can only print strings, right? So you can't print a float or an int or anything else with puts. Right? Printf is the function that can handle other types. So it works by accepting a formatting string that tells it how to interpret the other command line arguments. We'll look at this function in more detail later on. Right, and a main function returns an int. So this is different than Java, right? So Java main method does not return a value. In C, the main function is supposed to always return an int, right? The value that's returned is sets the exit status of the program, right? So remember, every command in Linux, when it's run, sets the exit status of the command, right? 0 means the command ran successfully. Non-zero means it did not run successfully. That number there is the exit status of a C program, at least in Unix or Linux, right? So returning 0 means that this program ran successfully without any errors. Oop. All right, what time is it? 1:05. Okay, so I'm going to go back to that compilation process here and talking about the preprocessor. Right. Okay, so if you the notebooks are whether you're using the notebooks or the lecture slides, it doesn't matter. They're both fine for the time being. If you look at the notebook though, where is my notebook? Here. Right. So a simple C program that basically covers what I just talked about in that lecture slide. The compiling notebook goes into a little bit more detail about what's going on when you compile the program. So let's take a quick look at that. Right. So compiling is basically the process of transforming code written in one language to another language. Right. In C, when you compile a program, at least the way that GCC works, is it takes 4 separate steps. Right. So first it does pre-processing. So it takes your source code and transforms your source code, but it's still C source code. The compilation process reads your source code, compiles it into, what does it compile it into? Compiles it into assembly language. Right. Assembly then takes your compiled code, does something with it. We'll get to that in a second. Right. And then finally, the last step is linking. So linking resolves the linking step basically connects all of the pieces of your program together. Right. So whatever functions you're calling, wherever they happen to live, the linking step deals with figuring out how to call those functions. So those are our hello world program. Right. The pre-processing step is the step where your source code gets read and things like comments get stripped out and your preprocessor directives get processed. Right. So anything starting with a hashtag is telling the preprocessor to do something. Right. The include directive tells the preprocessor to take the contents of the file and drop it into your program. Right. Now, GCC is kind of cool because you can grab the output of any one of these steps from GCC. Right. So if you use the -E option to GCC, right, that tells GCC to run the preprocessor and then stop. Right. So it doesn't actually compile your whole program. It just runs the preprocessor on your program. Right. Here I'm redirecting it to hello1.I, but if you don't redirect it, it's just going to print it to standard out. So let's try doing that and see what we get. So GCC -big E. Hello. It doesn't matter which one of these you pick, whichever one you like. And then redirect it to hello. The extension here is not standard. So I'm using .I for the preprocessor output. Okay, now we can look at what's in hello1.I. Okay, so let's take a look. Where is my main? Okay, there's our original program. Right, now remember, the very start of our program was that include standard io.h. Right, so all of this stuff that you're seeing here, right, keep on going, keep on going, keep on going. There's a lot of it. Right, the header file is quite long. There we go. Right. So starting here is where the compiler has dropped in the contents of the header file. Right. Not quite there. It's actually starting, I guess it is starting there. Right. And so you can see that the header file standard io.h is, there's a bunch of other stuff here as well. Where's the include? Here we go. Right. This is the start of the actual header file, standard io.h. Right. And you can scroll through. If you anything that isn't familiar to you, you just ignore for now, right? But you will eventually find something that looks familiar. Right. Oh, hey, there's printf. Right. So there's your declaration of the printf function. Right. And so when we use, if you were to use printf in your program and you included the header file, right, now the compiler knows, oh, hey, printf takes in that's a string, right, followed by a bunch of other 0 or more other arguments, right, of unknown type. Right. If you keep on looking, there's a puts somewhere. Hopefully I don't miss it. Puts, put W, F puts, there it is. So there's puts, right? It takes in a string. Right? And that's the only thing it takes in, right? So it can't take in an int, can't take in a double, can only take in a string, right? And so on and so on and so forth, right? And so you can see here that that include directive really did literally drop the contents of standard IO.h into our program. Right? And it left the rest of our program unchanged. Is there a comment in that program? Sorry, just let me. Hello, there is. There's a comment here. Notice that it got stripped out of our the preprocessor stripped out that comment when it processed the file. Right, the comment is missing from here. Okay, so the output of a preprocessor is something called a translation unit. Right, so if you're ever looking online and you see this phrase translation unit, it's basically that is the output of the preprocessor. Right, and so basically a translation unit, at least for the purposes of this course, consists of the C source code file and all of its header files that were included. Okay, the next step is compilation. Right, so after the preprocessor runs, the compiler now runs. Right, so the compiler transforms your C source code into something called assembly language, which you'll probably learn about a little bit in your architecture course. Right, assembly language is almost human readable. Well, I guess it's human readable. So it's human readable. It's not that easy to read. The commands in assembly language map closely to the commands that your CPU actually understands. Right, so they map to the target architecture's machine code instructions. If you want to, you can in fact look at the output of the compiler directly. So you can look at the assembly language produced by GCC. Right, to do that, you use the big S option. Oops, hello one. Okay, that produces a file, hello1.s, right, which is the assembly version of our hello world program. Right, and so notice that the commands. So this is the where's the data? This is the data section of our program. Our main function starts here, right? And notice that the commands that were in the C commands that were in our source code file, they get translated into this stuff here, right? Notice that it is readable, right? It actually sort of looks like English. What all these things actually do, who knows, right? I don't know assembly language at all, so I can't tell you what this is actually doing. Right? I can guess what that does, though, right? There's a assembly command called call, and there's our function puts, right? So that looks like the call to the puts function, right? Notice that in the compiled program, though, right, in the assembly language, right, there's no actual definition of the puts function, right? So our compiled program doesn't contain the definition of puts, right? It's nowhere to be seen here, or at least it doesn't look like it's anywhere to be seen here. Right, you would expect puts to be quite complicated because it's got to write stuff out to standard out, and it doesn't look like there's anything here. Right, and so the assembly version of our program is not a complete program. Right, there are people who do write in assembly language. Right, so you can learn how to write in assembly and write complete programs in assembly if you wanted to. It's painful, right? This is no fun writing in this kind of language. The people who do this sort of thing are normally writing high performance computing stuff, right? And so they're trying to write assembly code that is more efficient than the assembly code produced by a typical compiler, right? So things like computer graphics or anything super compute intensive, there might be small parts of your program that are actually written in assembly. Oh, right here. There's a little box that talks about that. All right, so now we've got our assembly program. Step 4 is the assembling process, right? And so in the assembly process, that human readable assembly code gets transformed into code that the machine can actually understand, right? So that code is called object code. You can look at the object code if you, oh, sorry. The object code, you can look at it. It won't make sense to you at all. It's all in binary, right? So you need some sort of program that can actually interpret the binary symbols correctly. You can tell the compiler to stop after the assembly process, and this is useful. It's not useful for this program, but it is useful in general, right? And so to tell the compiler to stop compiling after the assembly process, you use the -c option, right? And that produces the file hello1.o. So that's called the object file, right? So GCC -c hello.c. And so there is hello1.o. We can look at it we can try looking at it, but it's not going to look like anything sensible, right? Notice it's just a bunch of gibberish, right? And that's because the object file isn't in plain text anymore, right? It's been transformed into some sort of binary, and now you need something that can actually understand the binary symbols. Right. This is going to be useful for us later on when you start to build bigger programs, right? For a small program, you don't normally stop at this step, right? The final step is the linking step, right? And so in a typical C program, your C program isn't using only the functions that are that you've written yourself, right? Often you're going to be using, for example, one of the standard library functions, right? Those standard library functions have already been compiled for you and they live somewhere else, right? So they live in what's called a library file of some kind. So the final stage of the compilation process links your compiled program to any external libraries that were used, or to any other, it knits together all of your object code files so that function calls that live in other object files can be resolved. Right. So that's the linker step. Typically, this is another program that does the linking. Right. You normally don't take care of this step yourself, although you can if you want to. Normally, you don't do it. You let the compiler take care of it. Right. In our particular program, right? Remember when we looked at the output of when we looked at cat 1.s, when we looked at the assembly code, right? Remember there's our call to the puts function, but the puts function actually isn't here, right? It's the linker that resolves this call to puts, right? And brings in the puts function from the precompiled library file. Oops. Okay. Right. And so the entire compiling process, normally you just do it like this. Right. So normally when you compile a program into an executable program, you do it in one, for a small program, you can do it in one line. Right. And that does all of the steps for you. Right. Normally you don't stop the compiler at each stage. Right. You can if you want to, but normally you don't do that. Right. All right, so that's the introduction to C. I guess the next lecture we'll start to look at some of the features in C that you probably won't be familiar with yet from Java or Python. Okay. So that'll be on Friday, I guess. Yeah, Friday.
How you using the VS Code to compile and run? I'm not not just using the bench to compile the program.
Sorry, hang on a second here. I gotta.